Hey everyone, welcome back. There's two classes that remain in which I'll be doing most of the talking before we move over to presentations, and there are some rather nice presentations that are being prepared. I'm looking forward to them. Do please let me know if you're taking the class for credit and have yet to plan a presentation. Please do be in touch about that. Right at the get-go of the class, I specified a possible range of topics. I think we've come through 4 of those. 5 and 6 concern critical percolation, dynamics you can do on that, and connections to random double staircases. And then the topic 6 concerns Kadar, Parisi, Zhang universality random growth models and the way in which scaling limits of those can have fractal structure, including exceptional sets and local times and random double staircases. So the idea has been that I'll give one class piece to each of these topics 5 and 6. There was a 7th topic in the intro that concerned connections to dynamical systems and random double staircases. Insofar as we treat that interesting direction at all, it will be via Ruben's talk. Ruben's been looking into this throughout the semester, and it's a possible direction for his talk. Although there may be others, we'll see. Okay, so what actually happened is I'm going to give on, it's not this Saturday, it's next Saturday, a talk at the Southern California Probability Symposium. And that talk kind of bridges across the 2 topics. In a sense, the talk has other themes as well. So basically what I'm going to use is the talk slides I did as a backbone for presentation across the next 2 classes. The talk I'll give at this SoCal symposium is only a 50-minute talk. So I'm going to, I think I've got too much material for that. I'll be turning that into basically a 3-hour talk, so to speak. But what I'll be doing is jumping out of this presentation and going back to the regular notes to fill out details. For example, this talk will only rather briefly allude to critical percolation, although in a sense, the fundamental ideas around critical percolation and its analysis involving discrete Fourier analysis will be an element in this talk. So what I'll do is I'll jump out of this at certain moments and connect back into the random double staircase themes in the 2 venues. Each of these topics, by the way, I call them topics 5 and 6, but really each of them could be a graduate class in itself. And indeed, it's possible. I'm doing another graduate class next semester. Obviously, you're welcome to continue for that if you wish. And then I'm still debating with myself what to put into it. The ideas and themes in this talk, which have a certain degree of independent life relative to the theme of random double staircases, are one possible direction for that class. So, yeah, okay. I'll give, as I say, I'll give this talk to some extent as an inherent, intrinsic item, and then just jump out of it to connect into the themes of our class. So, so stability and chaos in last passage percolation. It's about dynamics. It's about a situation where you have an equilibrium measure that interests you, and you introduce a time dynamic that leaves that equilibrium measure invariant. So in that way, you get an uncountable number of copies of the equilibrium measure tied together in the dynamic time. And then that, I suppose, already bridges into a potential theme from our class, because you could have something that's 0 probability statically, but because you have uncountably many copies of the measure at exceptional times, the exceptional singular event could occur. And then you could ask questions about the Hausdorff dimension of the times when that happens, or you could build a local time, a singular measure that's supported on the exceptional times, and have a double staircase, a random double staircase. So it's work with Shishendu. It's quite a lot of work we've been doing for the last 18 months that's come to completion now. There are 2 papers on the archive. The main paper has exactly the title of this one, and then there's an important but auxiliary technical paper. I would just basically, probably the easiest thing if you want more details is just to remember some fragment of the title of this talk and then go to the archive and type that in. You can pull up the paper that way. Okay, so yes, it's quite a big topic. I had to decide how to get into this topic. One route in is to talk about energy landscapes. So when you have a discrete statistical mechanical system, well, it's kind of a truism that basically if you have a discrete probability measure, then the individual points are receiving positive mass, let's say. So if the measure is called mu, I can just say the mu value of any singleton is just notation to some extent to say it's e to the minus h. Now h is a Hamiltonian or an energy. So it's just notation so far. But it can be viewed as an energy that's kind of specified over a landscape. Or well, the precise thing that's the landscape, I don't know if it's kind of a language. Anyway, you can think of the underlying space as a landscape. So right, there's a picture of landscape geometry of a random system. So you have a sense of, I'm trying to draw out the themes of complexity here in this picture, and the notion that the system is likely to be near the energy minimum, the base of the deepest valley. You see e to the minus h. H will be as small as possible in the maximal energy and maximal probability configuration, and that's called the ground state. So in this picture, it's perhaps there in the corner. And then a theme that we'll be returning to is the notion that some systems may have kind of many energy minima, many value bases that are competitors, rivals to the status of the global minimum. Perhaps in some sense they come relatively close, and perhaps they do so in a geometrically rather distinct way. So when that happens, you have quite a complex picture, perhaps an interesting one of, you could imagine bobbling around at the base of one valley, and then in a longer time scale, the random particle moving around in the landscape is going to make its way over to a deeper valley, and it's going to do that in perhaps a rather characteristic way by moving over a hill, an intervening hill, but doing so doesn't like going up into high energy values. So it will sort of choose a route. You can imagine a traveler passing from one valley to the next, and on his route, you can imagine him on this arduous journey on the left and the right, seeing hills and walking over a mountain pass. And indeed, the term mountain pass is sometimes seen in these kind of analytic topics. So you see, at the top of the mountain pass, there'll be a saddle point. Imagine at the moment that the traveler is trying to go on the route between two valleys, and to pick the route that will keep his height as low as possible at its maximum. And that will involve passing to a saddle point at the peak of the journey. That will be a moment where he stops climbing and starts descending. But you could imagine that because it's the lowest route subject to these constraints, that on his left and on his right at that moment are hills. So in front of him is the valley he's approaching. Behind him is the valley he's departing. He's at the maximum moment, and to the left and the right are greater hills that he's somehow avoiding by choosing this route. So it's a saddle point. So that's just a connection to ideas, analytic ideas around, for example, Morse theory, topological ideas. But anyway, that's not really the direction I'm going. But anyway, the notion of several valleys or multiple valleys. So 3 natural questions about an energy landscape. Question 1, is the ground state energy super concentrated in variance? So if you have a classical situation of flipping a coin n times heads or tails, heads is 1, tails is 0, the variance of that situation is of order n, right? The typical deviation from the mean is root n, so the variance is order n. And broadly, do we have situations with a landscape where the actual energy, the height of the lowest level, the energy of the ground state is somehow got less wiggle room randomly, has less variance than this sort of classical situation? And I really haven't specified here very clearly what the parameters of this are. There'll be examples later, but it's just a general flavor for the time being, okay? Super concentration. Are there multiple valleys? Well, I've already told you something about that. Here's just a picture, several valleys that rival the ground state, perhaps with rather distinct geometry, perhaps in some sense rather displaced from the main valley. Are there genuine competitors? That's a question you can ask or try to formulate and ask. And then does chaos reign? Okay, so you could imagine, in some sense, noising the system a little bit, perturbing the system by a small amount of noise. Imagine critical percolation on the honeycomb lattice, on the faces of the honeycomb lattice, red and black in this description, each hexagon colored independently with probability 1/2. I haven't filled in the whole thing yet. Imagine that the blue hexagon here is going to perhaps be re-randomized in response to a tiny change in the noise in the system. We randomize just a few of the bits and we end up flipping the blue hexagon. This is a situation that's pivotal for the outcome. The outcome meaning, does red win or does black win? Is there a red connection from south to north? You can see the boundary is divided into 4 pieces, north, south, east, west, and north and south are red, west and east are black. So is there a red passage from south to north, or is there rather the mutually exclusive event of a black passage from east to west? The blue hexagon will decide everything because there is the 4-arm event. There are 4 arms, 2 in red emanating from the blue hexagon to the north and the south, and 2 in black to the east and the west. And they make the outcome at the blue hexagon, you know, Florida in 2000, everything hinges on it. Yeah. So at this point, I suppose I could actually stop and do my speech about the topic that I'm formally supposed to be talking about, which is indeed this. I actually have a slightly different official aim for this class, which is to tell you about the dynamical version of critical percolation on the honeycomb lattice and the sense in which the topics of the class around exceptional sets, Hausdorff dimension, random Devil staircases can emerge. So let me dive out of this, but kind of be inspired by this. Let me go back to, I'd rather stay in Notability, but go to our class note for today. So let's have a bit of a think about...
Can you stop sharing?
Oh, don't know why it does that really. Yeah, okay, so let's explore some of these themes for critical percolation. So, okay, as I say, I won't redraw that picture, I suppose. It's a half-half, each hexagons. Each hexagon is black or red, probability a half. Choices made independently. This is the critical value of percolation on this lattice, in the sense that if the probability of black were to rise by an arbitrarily small given amount, above a half, there would be, in the infinite lattice, almost surely, a unique black connected component. And in fact, if we were to drop instead away from 1/2, all of the black components would be finite, and there would, by duality argument, be, well, anyway, it's true that there would be a unique infinite red component. Those supercritical phases were the object of study in the preceding topic for a slightly different lattice. You know, that was a kind of our playground for discussing bias walk, was to work in an environment offered by the supercritical infinite cluster. Here we're actually fixing the value at the critical value. The situation at the critical value is, in fact, that there is no, in this lattice, there is no infinite structure in either black or red. All of the black and red clusters are finite. And so we can ask questions about the probability of having a large cluster in the first instance. So I'll just, I think, I won't bother drawing this lattice. It will take too long. What's the probability from the hexagon in the middle? I won't even really try and seriously draw that. What's the probability that, just choose one of the colors, black. What's the probability that the black cluster that contains this hexagon, I suppose I can at least attempt to draw a hexagon, I mean, it might be empty, it might be a red hexagon, but if it's black, then it's in a non-empty cluster. What's the probability that this cluster reaches to distance n, that it leaves this box? This is a topic that, this is called a one-arm event for more or less obvious reasons. I suppose there's a single arm that takes you off to infinity, or not to infinity, this is the side of this box. What's the probability that this happens? It's something that tends to 0 with n. So there's a great deal of theory that goes into this around a huge advance made at the end of the 90s by Oded Schramm was to introduce what he called stochastic Loebner evolution, and what many people now call, in his honor, Schramm-Loebner evolution. I don't think I am going to attempt to give you any kind of a description of these. They are a kind of beautiful class of conformally invariant stochastic processes that conjecturally, and in some cases, including this one rigorously, describe important aspects of the scaling limits of critical percolation and other critical two-dimensional systems that have conformal invariance properties. I'm just going to, I think, in fact, quote the kind of results you get from this. So there are very nice exponents that emerge in this theory, and the one-arm exponent is 5/48. I'm always a bit envious, I suppose, working in KPZ of the nice form they have of their exponents. Our exponents tend to be things like 1/3 and 2/3. They have rather fancy exponents. Yeah, I'm not really going to try and justify that, and I probably wouldn't be able to remember the justification offhand anyway. This is something that comes from the theory of SLE. I'm going to rather accept a couple of inputs from SLE with a view to kind of advocating the random devil staircase picture that we can get when we start doing a dynamical version of critical percolation on this lattice. So this is going to be one of two inputs, really, that are going to help us. So the other one is that let's do the same thing with a more elaborate event, something whose relevance we've already seen. What's the probability that the origin hexagon is pivotal for the question of whether black or red wins? So, you know, if I now choose this to be the black side, I think this is the opposite way around to before, but who cares? It's an n by n setup. And then it's going to be, if I can quickly go to red, it's going to be, you know, red is perhaps closed, black is open. Anyway, those are the colorings of the hexagons. So a four-arm event is one that is like this, and it's what renders the origin hexagon pivotal. It's drawn black here, but if its status is unknown, then it will just say who wins, which way the connection globally goes. What's the probability of that? Well, that's the four-arm event, and it's also an SLE computation to determine the decay rate for this. It's obviously going to be a faster decay rate than the one-arm event, and it decays like n to the minus 5/4. Plus little o of 1. This little o of 1, as in, I assume I used the little o of 1 notation before, this is in the high end limit in each case, okay? So these are vanishing probability events, but this is a quantification of what happens. So I'm just going to take those again, an SLE success, an SLE outcome, the four-arm event. I'm going to accept those as given rather, and just tell you a bit about how we can think about some of the ideas in our class given these very important inputs, okay? So I'm going to move to dynamical percolation.
I have a question.
Yeah.
So in the four-arm event, you're fixing a hexagon and then you're conditioning that the top and the bottom and the left and the right are black and red. Is that right?
You could say that way. I mean, to some extent, it just means, it's just a way of remembering. You don't really need to condition anything. You can just, it's just, I like to psychologically really just think of east and west as being the red boundaries, and then north and south as being the black boundaries, and then black is trying to, as it were, make it between his two boundaries, red between her two boundaries.
Right. So, okay.
I mean, you could say it's conditioning because everything's independent. So yeah, it doesn't actually affect this is a question about the random statistics of all the hexagons inside this square. So I suppose
Okay.
Yes, that would be fine to condition because it would remain independent in the middle.
Okay, got it.
Okay. So yeah, in the dynamical percolation of the model, it's just Poisson clocks. So there's a Poisson process of rate 1 attached to each hexagon. Okay, so this is maybe the origin hexagon. Any given hexagon independently has this. And then they are labeled, I suppose, red and black according to independent coin flips. And then, of course, when one of them rings, time is evolving from, let's say, time 0. When a given clock rings, you obviously recolor the hexagon according to the new label, and then that will endure until the next clock rings. So you have this kind of fluttering or shimmering throughout space of the status of hexagons, with each individual hexagon changing once per unit time on average. And then at any given moment, either red or black is winning, if you're interested in the problem of who's winning in this picture. So you can also ask questions, though, if you're interested in being at the origin and perhaps looking at the black cluster, then this will be a dynamically varying object that will quite often be rather small, but will occasionally flare up and become rather big. So an exceptional times question is, you see at time, we start the process at equilibrium. So at time 0, we simply decide what the status of all the hexagons, red or black, is with probability half independently, and then the system will be maintained at equilibrium by this dynamic. So at any given positive time, it will equally have the distribution of critical percolation statically. So we can ask questions like, what's the probability in an exceptional times question? Does there exist a time t in 0, 1 at which the cluster of the origin is infinite? The cluster of the origin, if that's just notation for that, is infinite. So this dynamically varying object is potentially infinite at certain times. There's 0 probability at a given time, but we have uncountably many copies in a sense. So in principle, it's possible that it is infinite. And in fact, that's true. And I suppose on the basis of the 2 exponents I've using as inputs, I can make some sort of intuitive case for why this is true. Let's, when we study things going off to infinity, very singular situations, we often find it convenient, and I think we have in the class, to use surrogates that in a sense fatten exceptional sets out a little bit. The times at which you go off to infinity is an exceptional singular set of measure 0, if it exists at all. In fact, it does, with positive probability. So, we saw perhaps with local time, if you have a process that's 0 and the exceptional set, then sometimes we find it convenient to consider a surrogate for the set, which is slightly flattened. For example, the collection of times the process is very low in absolute value. So the analog of that here is to consider times at which we go out to a big distance, n. So are there moments of time at which we go out to distance n? So I just want to kind of ask a question, how stable is this? It will take kind of a positive amount of time, dependent on n, for a single hexagon to ring in this situation. So it's not a singular situation. It will be a situation that endures for a positive random amount of time. But how long do we expect that to be? In a sense, you can view the one-arm connection that is establishing connection to the distance n as being made up on dyadic scales of, if I draw some dyadic scales here for this box, then the one arm, the arm has to sort of cut through all of them and be successful in connecting the sides. And the view is of those, the least stable one, the one that is least, most sensitive to noise, is likely to be the one that's furthest away. Near the origin, there's a limited number of bits, and it's conceivable that very near the origin, the situation can be basically stable for a unit of time, but things will be more sensitive as you move to the outer layer. So that's the focus somehow. I'll emphasize this by drawing this picture a bit differently. Let's focus kind of on the outer layer. So this is distances from the origin n and n over 2. So at a given moment of time, I have this, and then that situation will endure for a while. The situation that will render it unstable and liable to break is the forearm situation, in which I have this. So yeah, how often does this kind of thing happen, that we have this kind of connection? Well, you see, the number of opportunities for it to happen in an n by n box, this is an n by n box, so there's n squared opportunities for it to happen. And then each one has probability given by the forearm event. So this is a calculation of the mean number of pivotals at a given moment of time. I mean, perhaps it's slightly misleading the way I put it actually. What's actually going on is that it's typical that when a one-arm kind of connection forms through a space of size n, it's actually got a lot of pivotals typically. Or with positive probability, it has a positive number of pivotals. And when it does, it actually has a lot. So this picture is a touch misleading because there are actually usually many pivotals rather than just one. So this is the number. So this is based on the forearm. I'm using that input. So for there to be a pivotal in a particular place is n to the minus 5/4 probability. And then there's n squared opportunities. So as an average, we have quite a lot of pivotal points. So these line up along the route somehow. Pivotal edges can be, yeah, okay, they line up along the route, let's just say. So how long does it take before things fall apart? Well, it takes the reciprocal of this amount of time. This is the intuition. Time to fall apart, time for the connection to go and for the opposing kind of red connection to achieve a victory and circle and cut off the black cluster from the edge of the end box. This is going to be the reciprocal of each one of these, a little bit of a ticking time bomb running at rate 1. And then there's, it's the minimum of, they are exponential random variables. So there's n to the 3/4 exponential random variables ticking along, and it's just the minimum of those that is going to cut things off. So that's going to happen in time. The minimum of k exponential random variables of rate 1 is an exponential random variable of rate k. So we're dealing with a collectively ticking time bomb with an exponential rate of n to the 3/4. So that will ring in typically time of order this. So this is a sense then of the picture. In going out to distance n, how much time in Lebesgue measure, how much time in 0, 1 do we have this? Well, you see, the probability of it happening at a given moment, that's the one-armed event probability, and then it's at equilibrium. So we're just integrating that between 0 and 1. I guess it's Fubini. The amount of time is the one-armed probability. Okay. But then another question is, if you've got that happening at a given moment of time, suppose you have this picture, how long does it endure? How long does this situation endure of connection given it's happening at one moment? And that's the heuristic we just went through. So that's going to be for a period of n to the minus 3/4. Okay, so now we're in one of these situations where we have, a slightly smoothed out exceptional set, which is now positive but small measure. So this is all the times between 0 and 1 at which we connect a distance n. So the measure, the total time, is n to the minus 5 over 48, and the packages of time, it comes in little bundles of time. This is a package of time. This is another one, and this another one. Each one of these has length n to the minus 3/4. This is all obviously based on these two inputs. It would be a substantial and obviously interesting question to actually answer how we obtain those inputs. I'm just taking it as a given. So then we can do one of our little calculations in which we say that the number of packages needed to cover going to be one of these little mini Hausdorff dimension type calculations. If that's called capital N, then the total number times the individual package time has got to equal the total time. Okay, so N, the total number of packages needed is this. But then you see, mimicking the notion of Hausdorff dimension, we want to write that in the variable package time to the minus something. So, package time equals n to the minus 3/4 in order to give total time, this which is n to the minus times n. I'm basically wanting to say, yes, it's not total time. It's what I'm trying to do is to say package time raised to the minus question mark is equal to number of packages, which is n. So that is n to the 3/4 minus 5 over 48. So what number is question mark? Question mark is equal to, it's supposed to be a 1 here, is that right? It seems to be a minus 1 at the moment. That's because there's a minus sign here, that's fine. So it's plus 1, that's for this, minus 5 over 36 for that, taking into account the 3/4. You see? So that's what the Hausdorff dimension is, 31 over 36. That is the heuristic argument for the Hausdorff dimension of the times at which we have a connection to infinity. Hausdorff dimension of times in which the origin connects up to infinity is 31 over 36. It's actually an event that occurs only with positive probability within a 0, 1. It's pretty clear that you could just have a stasis around the origin with positive probability, nothing really flickering for local reasons near the origin, so you wouldn't connect to infinity. But absent that, if you have times at which you connect, this is in fact the probability. And this was proved by Garbon, Petter, and Schramm in a beautiful paper about, I suppose 15 years ago now in ACTA. So that speaks to some aspects of what we've been talking about in the class, right? An exceptional set arising in a natural context in which we identify Hausdorff dimension. If you want to develop themes a bit further towards the random devil staircase picture, it speaks to the question of a local time. Is there a kind of a clock that naturally ticks at the moments at which the connection to infinity forms? Yes, we constructed that with Garbon and Oded in a paper. It speaks to the question what it means to kind of select a uniform time at which we connect to infinity. And then that speaks to the question of what the configuration actually looks like at this time. This is a setting that's rich enough that there's a kind of a rich geometric question to ask about selecting a point according to the local time. What does the configuration looks like? There's an object called the incipient infinite cluster. You see, in these models, there's zero probability at a static time that the origin is connected to infinity. So it's a singular conditioning that has to be made sense of to speak of conditioning critical percolation on the presence of an infinite black structure containing the origin hexagon. But sense can be made of it by things not unrelated to what I've said, of taking a weak limit as you go out to distance n, of having the connection and taking n off to infinity. There's a way of assembling a random double staircase picture in this model, and then in some sense there's a local time which is kind of uniform measure on the times when you are connected to infinity, and then if you sample from that, then you have this kind of structure, which is something Keston introduced into critical percolation much earlier. Yeah, okay, so well, these are connections that are nice. I'm not sure I'll say more about them. It's been a bit of a whistle-stop tour, but you know, these could have been developed into a much more substantial part of the course. They could have even been the entire course, in the sense that SLE, these exponents, we could have pinned down how they're developed and looked at other connections as well. But I think I'll just maybe leave it as that, unless of course there's any questions.
Alan, is this Keston tree which arises here more or less, this infinite, this incipient infinite cluster?
Yeah,
you have a backbone and dangling side trees?
Yeah, that's right. That's right. There's a sense in which there's a backbone, and then as you, in a way, it's like moving through dyadic scales, and then a bit like in the topic that we just did, there's other structures that hang off that are a little bit similar to saying you have just more like finite trees that hang off. But when we did the topic of the bias, the topic we just finished, we had a firmly supercritical situation with the backbone, and then a firmly subcritical one with the traps. Here it's a more of a nuanced situation where, in a sense, the backbone and the other structures are kind of both at criticality in a way. So these structures are capable of being much bigger than the kinds of traps we saw. So the geometry of this object is less linear somehow. And people study things like doing random walks on the IIC. So you move along the backbone and into the trap, but you spend a lot of time in the traps. I think Shishendu has been investigating this with James Lee recently, developing results of Keston, that there's a subdiffusive behavior because you spend so much time in the traps in this model. This is sort of not with the bias, this is just a fairly symmetric walk. Anyway, that's, yeah, that's right. I mean, basically the IIC is just taking a very big percolation cluster conditioned to be very big and viewing it kind of from a random point. And then it has this kind of structure, roughly speaking. Now there's one, I say we're leaving this topic, that there is a fundamental tool though of discrete Fourier analysis that is needed to make rigorous sense of particularly the dynamical version of critical percolation. And there's something called the spectral sample that was an absolutely key technique in Oded's work on this, including in this paper with Gabor and Christoph. So I will, at least to some extent, get back to that, because I'll be talking about that in the context of the second topic, the sixth topic for this class, in some sense, the KVZ topic. So if I jump out of that and go back to this, that was all viewed from the, perspective of this talk is an aside. but anyway, that's kind of what's going on in this screen. So, I mean, in terms of the internal structure of this talk, I was asking the third of 3 questions about random energy landscapes and asking the question, does chaos reign? So chaos means sensitivity to slight perturbations of noise. And this is a situation that's extremely sensitive in a sense. Well, it's extremely sensitive to the change in the blue question mark hexagon. And then the system is, in fact, sensitive in a collective sense because there are many blue hexagons, in a sense. Imagine if the blue hexagon were red, say. Well, I don't know if you can see in this example, but with propitious inclusion of black hexagons in the right place, other red hexagons will become vulnerable. So there can be several, and indeed there are typically n to the 3/4 vulnerable pivotal question mark blue hexagons. So this is an example of chaos, sensitivity to slight perturbations of noise. Yeah, so does chaos reign then in terms of this view of a random energy landscape? Is the ground state its location in this, imagine this energy landscape in all its complexity, and imagine it's being perturbed by a little bit of noise, some valleys getting more or less deep, the jaggedness shimmering around. Is the ground state's royal status being jeopardized by even fairly small perturbations in noise? If so, we call that chaos. Noise sensitivity, as opposed to a more stable situation, which indeed tends to be called, go by the name of stable, if you didn't have this. All right, so Saurabh Chatterjee in 2014 wrote a monograph in which, for certain models of Gaussian disorder, maybe I won't say too much about what that means, but obviously at some level specifying things as we did with Brownian motion with Gaussian random variables. These 3 ideas that have come up in these 3 preceding questions of superconcentration, chaos, and multiple values are all, the following are equivalent type situations with these double arrows of implication. If one of them happens, the other 2 do. That's a general theme from this very nice work of Saurabh a few years ago. Okay, so yeah, so the goal of this talk I'll be giving in a little bit over a week is to understand the order of noise perturbation that heralds the onset of chaos in a dynamical form of last passage percolation, which I'm going to recall if you don't know what that is. So let's maybe start with, okay, so I build into this, I think, by next talking about, well, I need to tell you, I think, what last passage percolation is, and then my kind of conceit for this talk is to have a look at least at the meaning of the 3 questions and concepts in a particular model of last passage percolation, Bernoulli last passage percolation. So the model is quite straightforward in its definition. Bernoulli last passage percolation, it's similar to percolation really, I suppose, in the sense that the underlying randomness is 0, 1 bits. They're being assigned to all the vertices in the 2-dimensional Euclidean lattice. So each one of those little dots receives a 1 or a 0 as an outcome of a naturally independently flipped coin heads tails. Okay, so you've got a system of 1s and 0s, and there's a path that's called an upright path. It connects these 2 points, 0, 0 to n, n, and it receives an energy via this random environment. That is the sum of the values along the path encountered. Okay, so I didn't draw the values down, write the values down. Was that a hand being raised, Minam? Yeah, okay, but you see you get a value that way. We'll call that the energy of the path, right? So every upright path on this route, or for that matter any other route, will get an integer, non-negative integer energy in this manner from the given environment. So the geodesic is the path's definition on that route whose energy is maximum. And we say Mn is its energy, the geodesic energy, M for maximum. Yeah, the maximum. Now, there is a bit of a problem that the geodesic route is not necessarily unique, because it's kind of a discrete model. There could clearly be, people have proved, in fact, that there are exponentially many competitors. I mean, actually rarely achieving the energy in N. I'm introducing Bernoulli LPP because I'm hoping for this talk I give it will be a simpler model. So I sort of don't want to get distracted by these details. And in fact, this is a surrogate for the model we actually study, which is a more Gaussian model called Brownian last passage percolation, where you do have this uniqueness almost surely. So I just kind of want to ask you in some sense to suspend disbelief and just kind of believe that there's only one geodesic. We could do some funny little tricks with tie-breaking decisions or something to make there's only one geodesic. It's not really a very important point. I just want to be able to refer to gamma n as the best route. Its energy is Mn. So, okay, I have my 3 questions. I want to say at least something about what's going on. What's going on with superconcentration? So that's, let's study the statistic, which is Mn, the geodesic energy on this route of length n. So you see, to dominant order, that will naturally grow linearly. There's 2n vertices you go through. There's on any route, or maybe it's 2n plus 1. Something like that, 2n plus 1. And 2n plus 1 vertices of order 2n. And so it's pretty intuitive maybe that on your best route, the number that you'll succeed in picking up is linear, that's somewhat inevitable, and constant is actually between a 1 and 2 strictly. So if you had 1, that would be kind of what you would get if you just chose a given route, deterministically selected without regard to the random environment. But you have all of these choices, clearly exponentially many choices of route. So perhaps it's pretty intuitive that you can boost the value of A above 1. And indeed it is bigger than 1. Yeah, so then what happens is, I should clarify, by the way, I'm just using Bernoulli LPP in some sense slightly diluted way. I just think it's a nice means to express ideas simply. I then want to explain what's going on, but this is definitely not a model in which the strong conclusions that I'm stating on screens like this are known. Integrability is a special property of a limited number of LPP models for which these kind of conclusions can be reached. I'm just going to, again, ignore that and enjoy the opportunity to sort of discuss this model and what's expected of it for now. So what's expected is that the standard deviation, after you center Mn by this dominant linear growth rate, then you have a fluctuation of order n to the 1/3. So if you paste onto the side of that a random quantity that represents what's going on in a scaled sense, that Wn, W is a word I tend to use, weight, for scaled energy, really, that's the reason for W. So that ends up being, it's expected to be a tight but non-degenerate sequence of random variables. So that the variance of Mn in that sense is n to the 2/3, and that's much less than n. So that's a manifestation of superconcentration. If you took a given route, deterministically chosen from 0, 0 to nn, the behavior would be n plus some random quantity times root n. So the variance would be n, it'd be the classical CRT situation. And that's what's emphasized at the bottom of this screen. That's the sense in which it's super concentrated. Okay. So the energy, I'm going to indirectly get to the other 2 questions by developing a bit of the theme of what the energy landscape of last passage percolation means. Let's consider the correlation between geodesic energies for different routes. Let's begin at the origin, and in one case end at the classic location, NN, that we've seen so far. But let's consider a perturbed route in which we end at a location n plus x, comma n. So in this picture here, you've got it. You've got the black geodesic going on the route we've talked about, and then the blue geodesic dives off to reach a different location horizontally displaced. And there is this kind of tree structure about how that works, that the geodesics follow a shared route for a while and then dive off on their different routes. I think my computer is interrupting me very annoyingly with an update. I now need to, can you not see the screen, or you can see the screen?
It's visible.
Somehow my computer tried to offer me a software update and has now gone, and I can't see you anymore. Let me just, I suppose it's just a psychological thing. If you assure me you can see.
We can see it, yeah.
Yeah.
Yes, I see, sorry. Let me just, if I click here, oh, I see. Stupid. Okay, so yeah. So all right, so you've got these two different routes. So a natural question you can ask is, what scale of x do you need to get to a kind of a 50% situation for correlation? This is correlation of the geodesic energy on the two routes. So it's a function of x, right? When x is 0, there's 100% correlation. What is the scale where it's becoming interesting and non-trivial, the correlation? And the answer is that x is of order n to the 2/3. This is the conjectural belief statement, okay? So that then is an important kind of exponent, and that answer suggests a scaled picture for kind of an energy landscape. My three locations I've been talking about on the left of that picture are depicted, 0, 0 to these two alternative locations. Let's do an affine transformation with these respective endpoints. So the origin will stay where it will. The origin will stay where it is. The vertical coordinate will be squeezed by a factor of n. There'll be a kind of a shear, so that the n point now hovers directly above the origin, and then there'll be a further effect of a squeeze then by n to the 2/3 to bring that x value, which is n to the 2/3 on the left, to be equal to 1 on the right. So then this is kind of a nice scaled coordinate system in which to view what's going on. So the geodesics can be drawn on the left, and then they can kind of be mapped over and depicted in a scaled form over on the right. That's what happens in this picture. Okay, so the choice of the x being of unit order in this picture creates a kind of a situation in which the geodesics on the left are kind of meeting about halfway along. You know, it's on this n to the 2/3 displacement scale on which geodesics join up with macroscopic periods together and macroscopic periods apart. So when you draw them in the scaled units, imagine n is rather big, so we can't see the discrete structure anymore over on the right. There's a scale geodesics that are counterparts to the two you see over on the left. And I tend to use the word polymers for them. I'm not sure I'm entirely popular for doing that because the word polymer has other meanings, but anyway, a short phrase for scale geodesic. So you see, that's the picture, that's the scaling picture we have for the geometry of the situation, but it's also natural to think of the energies of the geodesics as having scaled forms. So you see the energy of the geodesic that goes up to the scaled location x has that form that's written in blue. Dominant term linear plus random multiple of n to the 1/3. And then that, as indicated in red, that's a random but unit order scaled energy, which I tend to call weight. So WNX. That refers to the, you see here, you've got a polymer, you can call it rho nx running up to x, and then it has a scaled energy or weight, kind of unit order, non-degenerate quantity, WNX. Is that at least roughly clear what's being defined and what's going on? Any questions? Making this transformation to scale coordinates, which is slightly, you know, something to get the head round. Yeah, all right. Well, here's another picture of it. Anyway, polymers and their scaled weights. So the scaled geodesics or polymers form a nice tree structure where everyone's going back to the same place, and by a form of polymer uniqueness that admittedly for this model isn't quite perfect, but basically when people join up as they stay going south, they stay together. So they form a nice tree. And you see in this picture, for any given X location, possible endpoint, what I can do down below is to plot the polymer weight to that value, WNX, you see it there. And then that can be plotted as a profile as X travels forwards and backwards along the horizontal line upstairs. So that then gives you a polymer weight profile, WN. Yeah, polymer weight profile. So sort of scaled geodesic energy profile, always starting at the origin, but ending at this variable scaled point, 1 unit ahead in the scale coordinates. Okay? So then, all right, if we take a high-end limit of this, I'm telling you about this because I'm telling you about the structure of the sort of scaled energy landscape of last passage percolation, and these questions about multiple valleys or, well, the 3 questions really, they have a lot of meaning to be phrased in these terms. So what happens as you take the high-end limit is you get WN becoming basically settling down in a statistical sense to become an object called, we can call it W, weight, but that's actually something called the parabolic Airy 2 process. So it's, yeah, well, what it is a process that it's globally a kind of parabolic object, that minus x squared term, but then the Airy 2 process itself is a stationary process that is looking pretty Brownian on unit order scales. So in terms of our energy landscape picture, we have a certain point at which the process reaches a maximum and has an energy peak, and then you can see fairly nearby there might be a rival peak. So the peak energy is corresponding to somehow the maximum energy one can get out of a geodesic if you're prepared to vary the endpoint horizontally. But that's the scaled location. The horizontal location there is the one you would go for. And then around that, you have more or less convincing competitors in energy. So the kinds of questions that relate to what we've been talking about, or anyway, natural questions about scaled energy landscape are, what's the probability of an event we could call near twin peaks that's a rival to within epsilon of the energy maximum at distance at least 1. So this is the answer to that. So this is the scaled weight profile, the parabolic Airy 2 process. And here's the event that there's a rival peak that in a sense does a really good job at getting to a small distance epsilon from the maximum, but it does so in a geometrically very distinct location, being at distance at least 1 away, you see. So that's a good example of the multiple valleys, and they now become multiple peaks phenomenon of a geometrically distinct rival. So what's the probability of that? Oh, I didn't actually write the answer. It's supposed to say answer, but it doesn't actually say what the answer is. Let me just add this. So this is, where shall I write this? This is of order epsilon is the answer. Yeah, okay, so the profile, you know, the kinds of, the proof idea is coming up. Well, the profile closely resembles Brownian motion on unit order scales. So the estimate is inherited from Brownian motion. I suppose in this context, I would have time to say something about that. If you have a Brownian motion anyway, the probability that it has this type of behavior within a given unit order window, you can see that it has a probability epsilon. Maybe I won't give that argument. If you're interested at some point, I can explain why that's true. It's something anyway that I'm trying to communicate basically, that in this perhaps rather complex process, the answer is actually inherited from Brownian motion. So why is that true? Why is it Brownian? So this is kind of something that's true on unit order scales for the parabolic Airy 2 process. And the answer to that broadly is that we can embed the parabolic Airy-2 process as the uppermost curve in an ensemble of random continuous curves. That's the parabolic Airy line ensemble. That's via something called the RSK correspondence, which is an important combinatorial aspect of the topic, KPZ universality. This is all located in the topic of Cadar, Parisi, Zhang universality, these sort of random growth models like large passage population. So anyway, there's this way of embedding. The top curve here is the same as before, but it gets embedded in a natural way. Well, the picture says 1,000 words, I suppose, right? So that ensemble of curves satisfies something called the Brownian-Gibbs property. What that basically means is, say if I take the top curve between -1 and +1 and just wipe it out, and then ask the question, given everything else that's still on the screen, what is the condition of distribution of the removed curve? It's given by a Brownian bridge with the two endpoints, given that they have to be conditioned to remain above the curve below. So there's a sense of avoidance and Brownianity being implicated into the structure of these curves. So if the curves keep a respectful distance from one another, then they should look pretty Brownian. So the Brownian-Gibbs property is a powerful tool for proving Brownianity of the Airy-2 process, and that's what we're talking about here. So the Twin Peaks probability is indeed of order epsilon by a rather detailed analysis that I undertook with Jake and Milland a year or two ago, that makes a rather strong assertion that the profile on a unit order scale is Brownian because of a long analysis using this Brownian-Gibbs property. And so indeed, you then inherit from a much simpler calculation for Brownian motion that you might want to think about, in a few minutes why this is true, that you have this order error epsilon. So this speaks to questions about multiple values and the degree to which the system has geometrically distinct but convincing rivals in energy to the best one. So that's something about superconcentration and something about multiple values. What of chaos? So for that, we need a model of noise perturbation of our static system. So in the static system, the bits are independently heads, tails, 1 and 0. In the dynamic model, we begin with that at time 0, randomly scattering the 1s and 0s and assigning them to the bits. But then we start updating them independently at rate 1 Poisson times, as in the percolation case. Each vertex in Z2 now comes equipped with a Poisson process defined on the non-negative reals at rate 1, and a further labeling of the little crosses you get when things ring as 1 or 0. And then you evolve time and you change status as you encounter rings and examine the associated status 1 or 0. Is that okay? That's dynamical Brownian LPP. It begins with a static copy at time 0. Vertices start fluttering in their status, and at any positive time, it's another static copy. So as for the percolation case, very similar. It's essentially exactly the same noise specification you would use to have a dynamical form of bond percolation in Z2. So you have uncountably many static copies coupled together. Okay, so yeah, well, all right, I could have referred to this slide in order to say these things. I'm going to be monitoring the geodesic, perhaps its geometry, and perhaps its energy as time evolves. So these now take the standard route now, 0, 0 to NN. So the geodesic gamma n now becomes a function of time. This is an initial value at time 0. Time will begin evolving. It will have its energy mn 0, and at a later time t, it will have become blue, black to blue, and it might have changed a little bit. It becomes gamma nt, and it has energy mnt. Just definitions, okay? So how to measure the fragility of these objects to the passage of time, the sensitivity of these objects as time evolves. So the energy, we could look at covariance or correlation between the geodesic energies at time 0 and at time t. That would be one way of measuring things. That presumably starts at an initial value. We've already, in effect, debated what that is. And then it presumably will drop as time goes on. When does it drop? Geodesic overlap, that's another view, a geometric view. I've now got black and brown, is it? Black and yellow for the two geodesics in the lower sketch at time 0 and t. I can look at the overlap of the geodesics, quite simply how many vertices are there in both geodesics. That's overlap, ONT. So there could be two different ways of measuring things that seem natural enough. And these are the kinds of pictures you might expect. That the covariance at time 0, that's just the variance for the individual geodesic energy. So we've said that that's n to the 2/3, so that's depicted here. But presumably, as time goes off to infinity, we get independence. We just get, after a while, completely independent environments. So there's no covariance, ultimately, between mn0 and mnt. So this is just a qualitative sketch of what will happen. As far as, at least the limit as t goes to infinity, it's qualitative. For overlap, again, qualitatively, what happens? Well, at time 0, the geodesics are just obviously equal, black and blue. So we start at order n. And in fact, the long-term behavior isn't a limit of 0 because there could be some overlap anyway, even between independent copies. You can present an argument that the overlap at time infinity should be n to the 2/3. The reason for that is basically that there's kind of n opportunities for overlap in terms of an advancing anti-diagonal. So if you just go somewhere in the middle with an anti-diagonal, you'd be looking to argue heuristically, non-rigorously perhaps, that the probability of overlap is n to the minus 2/3 in order to get this conclusion when you sum out over the levels. So why n to the 2/3? Well, it's very similar to the n to the 2/3 we saw in the value of x, that basically an individual geodesic has kind of n to the 2/3 locations that it can realistically go through the midlife line at the anti-diagonal line that represents the halfway point of the process, and go through an n to the 2/3 location. So two independent ones might have probability n to the minus 2/3 of meeting, multiply that by the entropy n in the number of anti-diagonal coordinates, and this is the heuristic conclusion you reach. So again, no quantification here. This is just an expectation of what will happen ultimately in this behavior. So can we quantify one or other picture here and get a theorem about that quantifies the moment of time, the scale of the moment of time, heralding the transition from stability to chaos in dynamical percolation? So it's actually the theorem with Shishendu is for Brownian last species percolation. In the talk I give, I think I'm not going to define it. I probably should say something here, because one thing I should be doing is setting up the groundwork for 3 talks I'm looking forward to from Eugene Milland and Mady, who will be speaking more or less directly about aspects of this, not always very directly, but let me just say what, yes, I don't need to leave Notability, I just need to go back to my other note. Yes, all right, so I just want to tell you what Brownian LPP is. I kind of want to say enough to kind of back up as an intro the talks that we'll hear about this, and also, of course, this theorem is actually for this model, so I suppose it's nice to hear. We have the same kind of setup in a sense. We just replace discrete Bernoulli randomness by continuous Gaussian randomness by Brownian motion. So we go on a journey from 0, 0 to n, n. And then what we have is on each coordinate, each intervening coordinate, we have a Brownian motion, just a rate 1 Brownian motion. It makes somehow no difference what the actual heights of the Brownian motion are, we're only concerned with increments, but I can sort of draw them starting at these levels partly just so that there's space. They can intersect one another. I'm just drawing for reasons of clarity, not too many intersections. So then what we do is we just, what is the geodesic, what is the energy? What is an upright path? So an upright path is a movement like this. Okay, so I suppose it's simply a non-decreasing map from 0n into the integer interval, 0 up to n. It's a non-decreasing map. That's an upright path. So the energy of an upright path, what you do is the energy of an upright path, you sum the increments. So there are these, as you enter the level 2, you have a Brownian motion that can be called B2. Suppose you join at x and leave at y, so you sum these increments up. So it's as if you, in a sense, your experience is you ride along each Brownian motion in turn, and then your value, your energetic value, is the sum of those increments you experience from here to here. So then the geodesic is the upright path of maximum energy. It's, in fact, in this model, almost surely unique, given the endpoints. And then you have everything else is sort of similar. If that object is called gamma n, it has these kind of behavior that I've been suggesting, that in the middle relative to the straight line between the endpoints, it has a discrepancy of n to the 2/3. And then we do exactly the scaling transformation as indicated to write it in scaled form. And it can have a scaled energy or weight using exactly the same formulas that we've seen. So all of this setup kind of works. And in fact, this is a setup that's much, much more viable for rigorous analysis, because connections to things like the RSK correspondence and the parabolic airy line ensemble and the Brownian-Gibbs property are all available. They're not available, in fact, in Bernoulli LPP. That's just a heuristic device. So yeah, okay, so that's just a brief indication of the definition and the meaning of notations for the actual model of rigorous study with Shishendu. Brownian loss passage calculation. So yeah, well then you do a dynamical version of that. Okay, well there's a natural way of putting a dynamics on a Brownian motion called an Ornstein-Uhlenbeck dynamics. I suppose we've done the things in the class that allow me to say what that is. But when we constructed Brownian motion with the Levy construction, we had this dyadic construction in which ultimately we had a countable system of independent standard Gaussian random variables, and then from that sequence you read off Brownian motion. So the sense of tenths that were at certain heights, and they were being picked according to Gaussian random variables, and then going to the next scale and having a little tent here, a little tent here, next scale down like this, 2, 4, 8 Gaussians coming off the shelf and being multiplied by these tenths added up to give you Brownian motion. So what you can do is start stimulating each of those Gaussians and making it into a more dynamical version. So there's an object called an Ornstein-Uhlenbeck process, which is a one-dimensional stochastic process. And what it does is it flutters around in a locally Brownian way, but it leaves invariant the Gaussian. So it's kind of a Brownian motion with a restoring force to keep it from drifting off. So if you imagine taking all of the Brownian, all of the Gaussian components in the Levy specification of Brownian motion and replacing them by these richer objects that are now processes, but leaving invariant the Gaussianity, you get a whole process in which you see a Brownian motion fluttering around, but being invariant. At any given time, it has the snapshot Brownian statistics, but it flutters around in time. So what you can do is use those processes as extensions of the, the Brownian randomness and the Brownian environment in this Brownian loss passage calculation. So that's something that then allows you to view geodesics and their scaled energies as functions of time, and to speak of overlap as a function of time. So the theorem then, which Shishendi says that for this dynamical version of Brownian loss passage calculation, we indeed have a transition from stability to chaos measured by a geodesic overlap, and it occurs at the key scale of time is n to the minus 2/3. So just a little bit more detail on what that means. So stability, if we're at time significantly below n to the minus 1/3, that basically means n to the minus 1/3 minus epsilon for a small given epsilon, then you are likely to have positive overlap. Okay, geodesic overlap is likely to be a positive proportion of the total, d times n. Positive proportion of the total is typical and is stable, but then it becomes chaotic as you move through this point and reach n to the minus 1/3 plus a small epsilon. Then the typical situation is that there is vanishing overlap at the level of the proportion. There's n, the total overlap can be as high as n, and it's actually dropped to be little lower there. Okay, so this is a fairly strongly quantified representation of the transition from stability to chaos in a dynamical form of LPP, a dynamical form of a model in the KPZ universality class. Yeah, well, I suppose we're coming close to the end now. Yeah, I suppose. Well, okay. One thing I want to be doing as I talk about this is to make some connections to the class. I actually want to talk about the ways in which we see fractal geometry in scaled versions of Brownian LPP, things like Devil's staircases. I could work off this material in a couple of ways to present examples of that. I mean, one is, maybe I'll just end today. Oh, I'm always jumping out of Notability, but I actually mean just to move to the notes.
Yeah, your screen stopped sharing.
Oh, okay, thanks. Shouldn't go back into Zoom, probably. Yeah, so, I mean, one connection we could make, having introduced these dynamics and spoken of near, twin peaks. We've talked about static twin peaks having a probability epsilon. One thing we could do is attempt to monitor the scaled evolution of this profile on this n to the minus 1/3 time scale and see that this scaled energy profile starts shimmering around. Does it?
Maybe it's just me, but we again don't see your screen.
Yeah, sorry, I don't know why it's doing that. Yeah, I particularly don't know that time why it stops. Anyway, oh, it's now jumped out again at the moment. That looks like a bit of a bug or something. The screen sharing ended unexpectedly. You may need to reboot this device if you cannot restart broadcasting to Zoom. I mean, given that that's unfortunate, I was only going back there to draw one sketch. I mean, basically, you could have this static scaled energy profile, parabolic ARE2 process, and then on this kind of time scale that's being identified by this theorem with Shishendu, you could sort of see how it's evolving and shimmering around. And then are there exceptional moments in time in which you actually get twin peaks? In a different context, Twin Peaks, the exceptional sets, Hausdorff dimension, that's something I've been exploring in work with Milland and Ivan Corwin, Konstantin Matetsky in a forthcoming preprint. It's a slightly different context to this, but we identify a Hausdorff dimension for that. That might be something you speak about. Is that right, Milland? Yeah. So, so this would be a bit different to that. It would be a different kind of dynamic, but you know, that's, you know, what's the Hausdorff dimension of times under the dynamic at which you have twin peaks? Can you put a local time on the exceptional set, and then it's a kind of leading to a random double staircase? These are questions that can be asked for this model. That's one of the connections we can make. There are other connections to fractal geometry that are actually a little bit different. Maybe I'll say something about that next time. Let me stop there for today.